say definition. Definition. If U is a subset of a vector space V, and it is also a vector space, then we say U is a subspace of V. Okay, it's a subset. Subset meaning that all the elements in U belong to V. But if not only being a subset, it's also a vector space, then we call that a vector subspace, or just in short, a subspace. Okay. Now, how many things do we have to check if such and such is a vector space?
8.
Huh?
8.
8. We have like 8 things that we have to check, right? So over a field, a vector space, a set is a vector space if it has vector addition and scalar multiplication, and the addition had to satisfy what identity, inverse, associativity, commutativity, right? Yeah. And then the scalar multiplication had to be compatible, meaning that A times BV was same as A times B times V. And then 1 times V didn't change V at all. So those are the 2 conditions for being compatible. And then the last one was you have to link the multiplication, scalar multiplication and the vector addition together. So there are 2 kinds of distributive properties you can write down, and that's it, right? So those are the 8. And if we had to use by the same standards for U, then it's a bit tough. However, because U is going to use the same scalar multiplication and the addition, I should really say this. It has to be a vector space using the same scalar multiplication and addition of V. All right? Yeah. So that's, I didn't write that, but that's like the unwritten thing. Yeah. Because you can also make a strange case where you just have a subset but define a new kind of multiplication and addition and make it a separate vector space. That would be strange. Okay. I mean, you could do that. So that's not allowed. So a second definition would be, maybe I'll just say theorem. If U is a subset of V that satisfies number 1, A, 0 is in U, B, for any U, V in U, U plus V is in U, and C for any lambda in F and U in U, lambda U is also in U. then U is a subspace. Okay. Now, let's try to see what each of these are. This is actually one of the conditions of being a vector space. This means additive identity should be there. That was one of the conditions for being a vector space. So that's directly from there. This one means if you take two elements in U and then if you add them together, it's still in U, it means that it's closed under addition. And this thing means you take any constant and multiply, any scalar and multiply to the vector, scalar times the vector is in U, so this means it's closed under scalar multiplication. Now if you have these, then it should be a vector space. Now, how do we prove this? Well, a lot of the things are not required to be proven because, for example, we already know that this addition is associative. We know that this scalar multiplication is compatible with the vector space. That's okay. The distributed property should be okay as well. Practically, the only thing that requires to be checked is, even commutative is still true, is whether the inverses exist. Okay. So let's just check that. Okay. So proof all properties of U being a vector space is clear, except if V is in U, there exists a W in U so that V plus W is 0. In other words, additive inverse exists. Okay. How do we show that statement? How do you know that additive inverse is always in U?
Isn't it implied by A?
Yeah, so proof is since -1 is in F and V is in U, property C implies that -1 times V equals to -V is in U. And that's the inverse. We showed that last time, right? The additive inverse of V is -1 times V. That's something that we showed last time. So that's it. Okay, so that allows us to really simplify checking if a given set is a subspace of V. To check something is to check whether a given set is a vector space requires you to go through all 8 items. So that's a really long and arduous process. But if you want to show that something's a subspace, you just have to check for 3 things. So it's a lot easier, okay? Now, notice that these 3 are not the only type of conditions that you would want, you can require. I mean, of course, you need these too, but this first condition can be replaced by, say, for any V, the additive inverse exists. That if you have those 3, then the same thing as saying that, because V plus -V according to 2 would satisfy this one as well. So there's some variance. Okay, so you can think of different ways to write just 3 conditions for something being a subset. Okay. All right. let's now write down some examples of subspace. Okay, number one, let's think about V equal to XYZ in R3. That's X plus Y plus Z equal to 0. Okay. Now in the review part, I've already said that this is a subspace, but I didn't really prove it. Now we can say this is a subspace because we have a clear definition of what a subspace is. So V is a subspace of R3. R3, because first of all, it is a subset, right? We're taking all the elements in V are from R3. It's just that we're taking these subsets where it satisfies that equation. Right? So let's check three things. First, is 0 in V? How would you know? Okay, so first of all, what is 0 in this context?
0, 0, 0.
0, 0, 0, right? So you just have to check. This is true because 0 plus 0 plus 0 is 0. Okay? So 0, 0, 0, by 0, 0, 0, in this context I mean this. We know that this is in V because it does satisfy this equation. Okay, now let's check any UV in V. That means U is like x1, y1, z1, and V is x2, y2, z2. Okay, I want you to think about the following. What condition should x1, y1, z1 satisfy?
C equals 0.
Because these are elements of this V, look at the definition, it must satisfy this condition, right? So you must satisfy x1 plus y1 plus z1. Same thing here. Now what are we trying to prove? If this is true, then we have to prove that U plus V is again V in V, right? That's what we are trying to prove. That's because U plus V, if you write them down, this is x1 plus x2, y1 plus y2, z1 plus z2. And if you add all of these together, we have to show that this is 0. To show that this is in V, you have to show that it satisfies this equation, right? For this equation to be satisfied, just take this one and plug in it to x, take this one and plug into y, take this one and plug into z, show that it is indeed equal to 0. Well, why is it equal to 0? Well, I can group this again as x1 plus y1 plus z1 plus x2 plus y2 plus z2. And this is indeed 0. And this is again 0 as well. Okay, so it is 0 and that means U plus V must be V. Okay. Yeah, it's constant going back and forth, like asking, what does this mean? And you should be answering, it means U is x1, y1, z1, where this is true. It means V is x2, y2, z2, where x2 plus y2 plus z2 equal to 0 because of this. Okay? And then now you ask the next question, what do I have to prove? Well, I'm in the process of showing that V is a subspace of R3. First condition is done. Second condition is that if U and V is in V, I have to show that the sum is again in V. So let's write down what that means. Okay? Write down what that means, and then you write down how you're going to show that this is in V. Well, you write the condition down, you see that, oh, I need to show that this plus this plus this has to equal to 0. How am I going to show it? Well, you have to use all the conditions that you know first. Well, I do know that x1 plus y1 plus z1 is 0, x2 plus y2 plus z2 is 0. Therefore, I can group them separately, and of course, I get 0. Okay? So that's how you solve this. And I think this is the major hurdle that people are finding when they take this class for the first time. It's that when it comes to proving stuff, there is no algorithm. There's only constant loop of asking questions to yourself and answering your own questions. Okay? You just have to have that loop constantly running. If you just see me doing something, then you wouldn't be able to master that art. You have to master the art of asking yourself a question and answering, all right? So let's write down the part C. If you pick any real number, okay, and any vector U, what are we trying to show? We want to show that lambda U is in V. Let's try that, okay? Well, lambda in R, you can't say much. It's just some real number. That's all we can say. How would you write this? U is in V. Well, that means, well, proof, U is in V means U is equal to what? X, Y, Z, where X plus Y plus Z is 0. Okay. X, Y, and Z are three numbers where they added to 0. Because that's the condition for V, right? Now, lambda U, what's that? That's lambda times X, Y, Z. And scalar multiplication in Rn is you just multiply to each components, right? This lambda X, lambda Y, lambda Z. That's what it means. Okay. Now at this point, stop and ask yourself, what am I trying to do again? Oh, I'm trying to show that this is in V. Well, that means I have to show that this is in V. How do I show anything is in V? Okay, let's see who else can answer this. Can someone answer this question? How do you show that this is in V?
X plus lambda y plus lambda z is 0.
Yeah, that's what it is, right? So, again, it's the same thing. If these three add up to 0, then the proof is done, right? But how do you show that this is 0? Well, factor the lambda out. And we already know that this is 0, so this lambda times 0, which is 0, so done. Okay. So that because of this, thus lambda U is in V. Done. Okay? So that shows you that it's a subspace. Okay, let's do this. I'm going to give you a second example, and you guys try to show that this is a subspace, okay? show this. But often, I think some people have trouble reading the set theoretical notation. Let me ask, is 1 comma 2 in U? Is that true? Is 1 comma 2 in U? No. Is x equals 1 and y equals to 2 in U? No, that's still no, because the elements in here are 4 numbers. Okay? So 1, 1, 2, 2 is in U. It's not these that's in U. Okay, it's this one that's in U. You get that? That's a distinction. You have to understand that distinction, or else you're not going to follow what I'm saying. See, in math, we're using exact language. We're not using everyday language. Every little detail counts. You have to see the difference. If you can't, then sorry, you can't learn proofs, right? So U contains elements that look like something, 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 with the additional condition that the first 2 coordinates must match, and the second 2 coordinates must match as well. Is that good? All right. So, give me an example of an element in U.
2255.
Yeah, 2, 2, 5, 5. By taking x as 2 and y as 5, you have 2, 2, 5, 5. Okay? How about -1, -1, 3, 3? True, by taking x as -1 and y as 3. How about 1, 2, 3, 4? No, why not? Because if 1, 2, 3, 4 can be written like this, x has to be 1, but at the same time x has to be 2. X cannot be 1 and 2 at the same time, so that's illegal. That means this 1, 2, 3, 4 is not in U. Okay. You have to first have the full understanding of what this set is before you prove anything. Problem is, a lot of you try to prove something without understanding what's in there, okay? All right, so once you have that, now the next thing is, let's show the 3 things. Number 1, I have to show that 0 is in U. Okay. And then we also have to show something like, if UV is in U, then U plus V is in U. And lastly, oh, I already wrote down C here. Yeah. If lambda is in R and U is in U, then lambda times U is also in U. So let's try to show these 3 things. Okay, in this context, the 0 in R4, this is a subset of R4, right? So 0 in R4 is 0, 0, 0, 0, so we have to show that 0, 0, so i.e. we want 0, 0, 0, 0 in U. Okay. Now we've already spent some time understanding what U is, so we can figure out that 0 is in U. Now is 0, 0, 0, 0 in U? Why? Because you can set x as 0 and y as 0. So that's exactly what you do. By setting x equal to 0, y equal to 0, we see that 0, 0, 0, 0, well, I'll even write this, okay, is x, 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 y, y, and anything that looks like this is indeed an element in U. So done. That's how you show it, right? Okay. Now let's try to show this. See, if you want to prove something, your assumption has to be in the form where you can make computations and make arguments, okay? So you better have U written as something and V written as something so that it's readily evident that it's in here. So for U to be in here, you better be writing down x, x, y, y. Same thing for here as well. But there's a problem with this approach. This, if you just write this, it means that U and V are the same vectors. That's not what we were trying to show. we have to show that for any two different, could be same, could be different, we don't know, but any vector, two vectors that you choose from U, their sum has to be in U. If we just go with this, then the proof will only cover the case when U and V are the same. So we have to be able to distinguish these two. How should we distinguish them?
Subscript.
Put subscripts. Write down x1, x1, y1, y1, x2, x2, y2, y2, just like that. And therefore, if you do u plus v, then because you're adding coordinate lines, that's how you add two vectors, right? So in Rn, the way you add two vectors is by coordinate wise addition. So you get x1 plus x2 as the first component, x1 plus x2 again, y1 plus y2, y1 plus y2. Okay? See, what I'm doing is exactly how you would do 1, 1, 2, 2 plus 3, 3, negative 1, negative 1. How would you add these? You would do 1 plus 3, 1 plus 3, 2 plus negative 1, 2 plus negative 1. That's exactly what I'm doing, right? It can't be different from this. It has to be this one, okay? Because we're doing this as a subset of the R4. Okay. Now tell me why this is in U. Is this clear that this is in U? Some would say this is clear. In fact, if you say, oh, therefore this is in U, in the exam, I would say, yeah, because you see that these two are the same and these two are the same, right? Yeah. But sometimes you might want to argue against people who are really stubborn against what you're trying to say. Okay? If somebody says, no, I still don't believe you, how are you going to show like 100% clear this is indeed in U? Well, you just have to find x and y that makes it into this pattern, right? So we take, well, let me give a different color. Use red. So we take U, no, not U. We take x as x1 plus y1 and y as x1 plus x2 and y as y1 plus y2. Then we see that u plus v can now be written as x, x, y, y. That clearly is an element of U. Done. Right? So nobody will be able to argue against that. That's 100% clear. Right? Okay. For this here, we have, again, you write U as x1, x1, y1, y1, so that lambda times U is lambda times x1, x1, y1, y1. That's equal to lambda x1, lambda x1, lambda y1. Okay, so now in order to make this look like this, I should set x as lambda x1 and y as lambda y1. Okay? And that tells us that, and we have lambda times u, which is that, and that's really x, x, y, right? Since this is x, that's y, we can rewrite it like that, and we finished showing that this is mu. Okay? 3. Okay. Can somebody tell me what this meant? R with 0, 1? So if I add A to B, that means like A cross A cross A with elements of B. So that means like for each element of B, you have a value in each one of these. Okay, that's what we're collecting, right? Yeah. What is that? That's the set of all functions. Okay. Set of all functions from B to A. So I explained that last time. So R01, according to this one, means it's a set of all the functions from 0, 1, the interval 0, 1 to R. So it's a real valued function of R0 to 1. Okay. Now there are many different functions that's in here. So you could have from 0 to 1. You can have something like this, or you can also have something like this with some function that's disconnected. You might even be able to have something like that's going up, but then you have a solid value and come down here. So you have like all kinds of different possible functions from 0 to 1. And last time I explained why this set, all the functions, form a vector space. And now I'm trying to say the set of continuous functions from 0, 1 to R is again a vector space. Why is that? Okay, first of all, is 0 in here? What is 0 in this space?
Function that maps everything to 0.
Yeah, the 0 constant function of 0. Okay, yeah, definitely that's continuous. So it's in this subspace, right? Subset. Okay, if you have two continuous functions, if you add two continuous functions, is it a continuous function? That's true. If you take any continuous function and multiply by a constant, is that a continuous function? That's true too, right? Okay, so that's true. And then, how about differentiable functions? Is a subspace of R to R. So if you collect all the functions from real numbers to real numbers, and if you think about only the subset that collects differentiable ones, differentiable means it has to be all connected, it has to be continuous, and at every point, tangent line should be defined, which means that you can't have sharp turns. Okay, and it has to be continuous and no sharp turns. If you collect those, it will again be a subspace. Okay. All right. Another nice example is when you have so consider C infinity, which is A1, A2, infinite sequence where AI is in C. Okay. Then this is a vector space, because obviously you can have 0, 0, 0, 0, and then it's like Rn, but n is infinity. Yeah. And instead of R, you have C. Now, then V, where again we're collecting the same type of things, but with the additional condition that AI is not only in C, but limit of n going to infinity of an is 0. So sequences that converge to 0. That's again a vector space. It's a subspace. So now note, what about W Okay, is this a subspace of C infinity? What do you think? Is this a subspace?
No.
Why not?
Zero's not in it?
Because 0 is not in it, right? So if this is a subspace, you better have 0, 0, 0, 0 included in here, but think about that sequence, 0, 0, 0, 0, 0. What's the limit?
0.
The limit of that is 0. It doesn't satisfy this, so it's not in here. So this is only a subset of C infinity, it's not a subspace. Okay? Okay. So, number 6. If V in V has F 0 to 3 to R with the F prime of B, sorry, F prime of 2 equals to B is a subspace of R 0, 3. What is B equal to? Again, this means it's a set of functions from the open interval 0, 3 to the real numbers, right? And you're collecting only those who are differentiable at 2. And if you collect them, that's equal to specific value. Is this always a subspace? No. B has to be a specific value. What do you think B should be? Well, to have this, you better have the 0 in V, right? What is 0 in this context?
Function F over
Constant
0.
function 0, right? Now for that function, what's F prime of 2?
0.
0. So the answer is B has to be 0. Because if this is not met, then you wouldn't this set wouldn't have 0 in there, so it won't be a vector space.